On a clear night, far from city lights, you can see approximately 5,000 stars with the naked eye. They span the sky in every direction, some brilliant and steady, some faint and flickering, some clustered into patterns that human beings have been naming for thousands of years. They look like they are all roughly the same distance away, like lights pinned to the inside surface of a dome. For most of human history, that impression was not just the intuitive interpretation, it was the scientific consensus. The stars were fixed, equidistant, arranged on a celestial sphere that rotated around the Earth once per day. The sphere was real. The distances were all the same. We now know that this picture is spectacularly wrong. The stars are not equidistant. They are not fixed to a sphere. They are scattered through three-dimensional space at distances that vary by factors of thousands, tens of thousands, hundreds of thousands. The faintest star you can barely detect on a clear night may be closer to Earth than some of the brilliant ones blazing near the zenith. The night sky is not a flat painting. It is a deep field, a three-dimensional landscape of unequal distances, in which the stars you see together are often not together at all, separated by light years of empty space even when they appear, from Earth to sit side by side. And some of those stars are dramatically closer than others. Not closer in a way you can see with the naked eye. The light from even the nearest star takes more than 4 years to reach us. And no unaided human sense can perceive a difference between 4 light years and 100 light years, but closer in a way that matters enormously for physics, for the search for habitable planets, for the remote possibility of interstellar travel, and for the basic question of what our cosmic neighborhood actually looks like when you map it carefully and honestly. This video is about the nearest stars, not the brightest stars in the sky. Those are mostly distant giants blazing brilliantly across hundreds of light years because they are genuinely extraordinarily luminous, not because they are close. The nearest stars are a different and stranger collection, mostly dim, mostly red, mostly invisible to the naked eye, clustered within a bubble of space about 15 light years, in radius that constitutes our immediate cosmic neighborhood. They are not glamorous. Most of them could not be seen from Earth without a telescope, but they are ours. The stars of the near neighborhood, the ones whose light reaches us first, whose gravitational influence is most direct, whose planetary systems, several of which now have confirmed planets, are the nearest examples of other solar systems to our own. We are going to travel through this neighborhood star by star, beginning at home and moving outward in order of distance. The way you might walk through a map of your town, starting from your front door. At each stop, we will look at the star in detail, what type it is, how it compares to the sun, what we know about its planets, what makes it scientifically interesting, and what it would look like if you could stand in its light. By the end of this video, you will have a precise, detailed picture of the solar neighborhood that most people, even most science enthusiasts, do not have. Because most people know the names of the bright stars, not the near ones. And the near ones are the ones that matter most. Before we start, there is one thing about the nearby star census that is worth knowing in advance, because it will shape everything that follows. Of the 20 or so nearest stellar systems to the Sun, the stars within about 13 light years, the overwhelming majority are red dwarf stars. Small, faint, cool, long-lived M-type stars that barely register in the night sky despite their proximity. There are a handful of exceptions, Sirius, Procyon, and a few others, but the dominant character of the solar neighborhood is red dwarfs. This is not a coincidence. Red dwarfs are by far the most common type of star in the Milky Way, constituting approximately 70 to 75% of all stars in the galaxy. The bright, sun-like stars that dominate the night sky are a biased sample. They are visible precisely because they are intrinsically brilliant, and most of them are much farther away than the nearest red dwarfs. The true picture of the galactic stellar population and of our own immediate neighborhood is dominated by dim, red, long-lived stars that you cannot see without a telescope. This fact has profound implications for the search for habitable planets and the distribution of life, and it becomes more important with each new star we examine in this tour. Let's start at home and work outward. Chapter 1: How we measure stellar distances. The ruler that built the map. Before we can talk about which stars are nearest to Earth, we need to talk about how we know. The distances to stars are not directly measurable in the way you measure the distance across a room or even across a continent. No ruler reaches to the stars. No radar signal bounces off them and returns in a measurable time. Not because the idea is wrong in principle, but because the round-trip time for a radar signal to Alpha Centauri and back would be 8.48 years, and the signal would be diluted by distance to a level far below detectability. So how do we measure stellar distances? The primary method for nearby stars is parallax, a technique so elegant and so ancient in its underlying geometry that it is worth spending a moment with before we launch into the star list. Hold your finger up at arm's length and look at it first with your left eye closed, then with your right eye closed. Your finger appears to shift position against the background. The apparent shift, the parallax, is caused by the slightly different viewing angles of your two eyes, separated by the roughly 6.5 centimeters of the distance between them. Your brain automatically uses this parallax to construct a sense of depth and distance. The larger the parallax, the closer the object. Stellar parallax works on exactly the same principle, but uses a much larger baseline, the diameter of Earth's orbit. Instead of the 6.5 centimeters between your eyes, the baseline is the 300 million kilometers of the full diameter of Earth's orbit around the Sun. We measure the apparent position of a nearby star against the background of more distant stars in January. Then measure it again in July. 6 months later, when Earth is on the opposite side of the Sun, 300 million kilometers away from where it was. Nearby stars shift slightly against the background. The amount of the shift, the parallax angle, is inversely proportional to the distance. The unit of distance derived from this technique is the parsec, defined as the distance at which a star would show a parallax of exactly 1 arcsecond, 1/3600th of a degree. 1 parsec is approximately 3.26 light years, or about 30.9 trillion kilometers. No star is close enough to show a parallax of a full arcsecond. Even the nearest star, Proxima Centauri, shows a parallax of only 0.7687 arcseconds, placing it at a distance of 1.295 parsecs, or 4.24 light years. The parallax of even the nearest star is less than 1 arcsecond, a tiny, tiny angle. Measuring such small angles requires extraordinary precision. From the ground, atmospheric turbulence limits the precision of angle measurements to about 0.01 arcseconds, which means ground-based parallax can reliably measure distances only out to about 100 parsecs, 326 light-years. For the nearest stars, this is entirely adequate. But the real revolution in stellar distance measurement came from space. The Hipparcos satellite, launched by the European Space Agency in 1989 and operational until 1993, measured parallaxes for about 120,000 stars with an accuracy of about 1 milliarcsecond. 1,000 times better than ground-based observations. Its successor, the Gaia spacecraft, launched in 2013 and still operational, has measured parallaxes for over 1.8 billion stars with accuracies as good as 7 microarcseconds for the brightest targets. A precision so extraordinary that Gaia can measure stellar distances reliably out to several thousand parsecs, and has essentially mapped the three-dimensional structure of a significant fraction of the Milky Way. The distances to the nearest stars that we will discuss in this video are known to extraordinary precision, some to better than 0.01%. Thanks to Gaia data combined with earlier Hipparcos measurements and ground-based observations. There is one more thing worth understanding about stellar distances before we begin the tour: the relationship between distance and what we see. When we say that Proxima Centauri is 4.24 light-years away, we mean that the light we currently receive from Proxima left that star 4.24 years ago. We are not seeing Proxima as it is now. We are seeing it as it was 4.24 years in the past. For the nearest stars, this light travel delay is modest and largely irrelevant for practical purposes. For more distant stars, it becomes more significant. But for all stars, there is this fundamental epistemic gap between observation and reality. The sky is not a real-time image. It is a collection of signals from different distances, all arriving simultaneously at our eyes, representing different moments in the past. The nearest stars past and the most distant stars past are separated by billions of years, and we see them all at once projected onto the same flat sky. The map of the nearby stars is therefore also a map of the immediate past, a portrait of our cosmic neighborhood as it was a handful of years ago, which for the nearest stars is about as close to now as any astronomical observation can get. With that foundation established, let us begin the tour. Distance, order, starting from the closest. Chapter 2, Proxima Centauri, our nearest stellar neighbor distance from Earth, 4.2441 light-years, 1.2948 parsecs. Constellation, Centaurus star, type, red dwarf, M5.5 VE. The nearest star to the Sun is not one of the brilliant points you see easily in the night sky. It is not visible to the naked eye at all from most locations. Proxima Centauri is a dim red dwarf, a small, cool, faint star, located in the southern constellation Centaurus, not far in apparent position from the much brighter Alpha Centauri system. To see Proxima, you need a telescope. Even then, it appears as an unremarkable reddish point of light, conspicuous not for its appearance, but for its motion. It moves noticeably across the sky relative to distant background stars, over the course of years, a telltale sign of a nearby star whose parallax and proper motion are both measurable. Proxima Centauri was discovered in 1915 by the Scottish astronomer Robert Innes at the Union Observatory in Johannesburg, who noticed its large proper motion and correctly identified it as the nearest star. Proxima means nearest in Latin. The name is a description, not a label. Proxima is a red dwarf of spectral type M5.5 VE, the M indicating it is a cool red star, the 5.5 indicating it is on the cooler end of the M dwarf scale, the V indicating it is a main sequence star, as opposed to a giant or subgiant, and the E indicating it shows emission lines in its spectrum, evidence of magnetic activity and flaring. And Proxima is indeed a flare star. It produces frequent, powerful stellar flares, sudden and dramatic increases in brightness caused by magnetic reconnection events in its corona. These flares can briefly increase Proxima's luminosity by a factor of several, emitting intense ultraviolet and X-ray radiation. For any planet orbiting in Proxima's habitable zone, this flare activity is a significant concern for surface habitability. Proxima's physical properties represent a dramatic departure from the Sun. Its mass is about 0.1221 solar masses, roughly 1/8 the mass of the Sun. Its radius is about 0.1542 solar radii, just over 15% of the Sun's radius. Its surface temperature is approximately 3,042 Kelvin, compared to the Sun's 5,778 Kelvin, making it considerably cooler and redder. Its luminosity, total energy output, is approximately 0.00155 solar luminosities, meaning it emits only about 1/6 of 1% of the energy the Sun produces. This extraordinary faintness is the direct consequence of its low mass. Smaller stars burn their hydrogen fuel at a much lower rate than larger stars, producing far less energy per unit time. Despite its faintness, Proxima has one crucial advantage over more massive stars: longevity. Massive stars burn through their fuel quickly and live short lives. Some of the most massive stars in the galaxy live only a few million years before exploding as supernovae. Stars like the Sun live about 10 billion years. Proxima Centauri, because of its low luminosity and slow rate of hydrogen consumption, is expected to live for approximately 4 trillion years, almost 300 times the current age of the universe. Proxima has barely begun its life. In cosmic terms, it is a newborn. Any planets orbiting Proxima have the potential for extraordinarily long periods of stellar stability, provided they can handle the flare environment. And Proxima does have confirmed planets. The most celebrated is Proxima Centauri b, confirmed in 2016 through radial velocity measurements by the European Southern Observatory. Proxima b has a minimum mass of approximately 1.07 Earth masses. It is at minimum an Earth-sized planet, and possibly somewhat larger, depending on its orbital inclination. It orbits Proxima at a distance of approximately 0.0485 astronomical units, just under 5% of the Earth-Sun distance. This seems extraordinarily close, but because Proxima is so faint, this distance places Proxima b in the star's habitable zone. The range of distances where liquid water could theoretically exist on the surface. Proxima b is one of the most discussed potentially habitable planets discovered to date. and the discussion is genuinely complex. On the positive side, it is Earth mass in the habitable zone, and at 4.24 light-years, it is the closest known potentially habitable planet to Earth. On the negative side, its orbital distance means it is almost certainly tidally locked. One face permanently toward Proxima, one permanently away, with one hemisphere in eternal scorching day and one in eternal freezing night. The flare environment is intense. Studies have suggested that the UV flux on Proxima b during a major flare event can be hundreds to thousands of times the UV flux on Earth during normal solar conditions. Whether life or even liquid water could survive, these conditions depends on factors we do not yet know. The nature of Proxima b's atmosphere, if it has one, whether it has a magnetic field, and what evolutionary adaptations might be possible given billions of years of exposure. In 2020, a second planet candidate was announced, Proxima c, at a much larger orbital distance of approximately 1.5 astronomical units, with a mass of several Earth masses. Proxima c would be far outside the habitable zone, too cold at that distance from such a faint star, and is too distant to be tidally locked. Its conformation is less certain than Proxima b's, and it remains a candidate rather than a confirmed detection. There is also evidence, tentative and debated, for a third signal in the Proxima radial velocity data at an orbital period of about 5 days, which would place this potential planet extremely close to the star. This candidate, if real, would be one of the closest planets to its star of any confirmed system. From a distance, Proxima Centauri would look nothing like our Sun. Standing on a hypothetical planet of Proxima, even one in the habitable zone, the star would appear as a deep orange-red disk in the sky, about 3 times the angular size of the Sun as seen from Earth, because of how close the habitable zone is, but shining with an eerie, dim redness rather than the brilliant white-yellow of our Sun. The sky would be dimmer than Earth's, though still lit because the habitable zone orbital distance places you close enough to receive roughly Earth-equivalent total energy. But the spectral distribution of that energy is very different from sunlight. More red, more infrared, much less blue and ultraviolet, except during flares. Plants on a Proxima world, if they exist, would likely not be green. They would be adapted to absorb the red and near-infrared wavelengths that Proxima emits most abundantly, and might appear black or dark red, maximizing absorption of the available light. Proxima Centauri is also notable as the target of one of the most ambitious interstellar mission proposals ever seriously studied, the Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking, entrepreneur Yuri Milner, and Mark Zuckerberg, proposed sending a fleet of tiny sail-bearing spacecraft, nanocraft, or starships, to the Alpha Centauri system and potentially Proxima specifically, using a ground-based laser array to accelerate them to approximately 20% of the speed of light. At this speed, the journey would take about 20 years. The spacecraft would be gram-scale, the size of a postage stamp, and would carry miniaturized cameras, communication equipment, and scientific instruments. They would fly through the system and transmit data back, giving us our first close-up look at Proxima and its planets. The proposal remains speculative. The engineering challenges are enormous, from the laser power required, on the order of 100 gigawatts focused on each sail for minutes, to the communication of results from 4.24 light-years away using a small transmitter. But it is the most physics-legal interstellar mission proposal that has received serious engineering study, and Proxima's proximity makes it the natural target. Chapter 3: The Alpha Centauri System, a triple star next-door distance from Earth, 4.37 light-years, Alpha Centauri A and B. Constellation: Centaurus star types, Alpha Centauri A, G2V, Sun-like, Alpha Centauri B, K1V, Orange Dwarf. Proxima Centauri is the nearest star, but it is almost certainly gravitationally bound to the Alpha Centauri system, a pair of stars locked in a mutual orbit at a distance of approximately 4.37 light-years from Earth. Together, Proxima and the Alpha Centauri pair form a triple star system, 3 stars sharing a gravitational destiny, with Proxima in a wide, loosely bound orbit around the central pair. Alpha Centauri A and B orbit each other at an average separation of about 23 astronomical units, roughly the distance from the Sun to Uranus, in an elliptical orbit that takes approximately 79.9 years to complete. This relatively close mutual orbit, combined with the eccentricity of the orbit, which ranges from about 11 astronomical units at closest approach to about 36 astronomical units at maximum separation, means that each star feels the gravitational influence of the other significantly. The stability of planetary orbits around either star is constrained by this mutual gravitational influence. Stable planetary orbits must be well inside a certain distance from each star to avoid being disrupted by the companion's gravity. The generally accepted stable zone for planets around Alpha Centauri A is within about 3 astronomical units of the star, and similarly for Alpha Centauri B. Alpha Centauri A is the more Sun-like of the pair. It has a mass of approximately 1.1 solar masses, a radius of approximately 1.22 solar radii, a surface temperature of approximately 5,790 Kelvin, and a luminosity of approximately 1.519 solar luminosities. It is, in other words, a slightly larger, slightly hotter, somewhat brighter version of the Sun, a G-type main sequence star of the same broad class as our own. From Earth, Alpha Centauri A is the 4th brightest star in the night sky, though it cannot be individually resolved from Alpha Centauri B without binoculars or a telescope. The pair appears as a single bright point at most locations. Alpha Centauri A is older than the Sun by about 1.4 billion years, estimated at approximately 6 billion years old, compared to the Sun's 4.6 billion years. This means that if Alpha Centauri A has an Earth-like planet in its habitable zone, that planet has had 1.4 billion more years to develop life than Earth has. An interesting thought: Alpha Centauri B is smaller, cooler, and less luminous than A. Its mass is approximately 0.907 solar masses, its radius approximately 0.865 solar radii, its surface temperature approximately 5,260 Kelvin, noticeably cooler and more orange than the Sun, and its luminosity approximately 0.5 solar luminosities. It is a K-type main sequence star, slightly smaller and cooler than the Sun, but not dramatically so. K-dwarfs are actually considered by some astrobiologists to be optimal hosts for habitable planets. They are more stable than M-dwarfs, fewer flares, less intense ultraviolet radiation. Live longer than G-dwarfs, allowing more time for life to develop, and have habitable zones at distances and orbital periods that are more favorable than M-dwarfs for planetary surface conditions. The question of whether Alpha Centauri A or B has planets has been a source of significant scientific excitement and frustration. In 2012, a team led by Xavier Dumusc announced the detection of a planet around Alpha Centauri B, Alpha Centauri BB, using radial velocity measurements. The planet was reported to have a mass of approximately 1.13 Earth masses in a very close orbit. The announcement was widely covered, but subsequent analysis revealed that the signal was likely a statistical artifact in the data, a periodic signal produced by the analysis method rather than by an actual planet. The detection was retracted, and Alpha Centauri BB is no longer considered a confirmed planet. More recently, the search has continued with better tools. The Ptolemy mission, a small space telescope specifically designed to search for planets around Alpha Centauri A and B using astrometry, measuring the wobble of the star's position against background stars due to a planet's gravitational tug, was planned as a dedicated search for planets in this system. The Breakthrough Initiatives funded preliminary work on this mission. Additionally, the European Southern Observatory's Espresso spectrograph, the most precise radial velocity instrument ever built, and the Near New Earths in the Alpha Centauri region project have conducted dedicated searches for planets in the Alpha Centauri system. As of the most recent searches, no confirmed planets have been found around Alpha Centauri, A or B, though the searches continue, and the non-detection does not mean planets do not exist. It means any planets present are below current detection thresholds. What would it be like to stand in the Alpha Centauri system? This is an unusual thought experiment because Alpha Centauri has two bright sun-like stars. From a planet orbiting Alpha Centauri A in the habitable zone, Alpha Centauri B would appear in the sky as a brilliant star, far brighter than any star in Earth's night sky, but not bright enough to illuminate a night hemisphere the way a moon does. During the 79.9-year orbital period, Alpha Centauri B would vary in apparent brightness and angular separation as the two stars moved through their orbit. At closest approach, B would appear nearly as bright as a crescent moon, a second, smaller sun in the sky. At maximum separation, it would still be the brightest star in the sky by a large margin, about 5 times brighter than Venus at its brightest as seen from Earth. The sky of an Alpha Centauri planet would have a second sun, not warm enough to cast shadows of its own from the habitable zone of A, but brilliant and unmistakable, a constant reminder that this is a binary system. The Alpha Centauri system is the subject of perhaps more speculative interest than any other stellar system beyond the Sun. It is close enough to study in extraordinary detail with modern telescopes, sun-like enough to be plausibly habitable, and old enough to have given life substantial time to develop. It has inspired more science fiction than perhaps any other stellar destination. The universe of Avatar is set at Alpha Centauri, and numerous other science fiction works use it as the nearest accessible stellar neighborhood. The fact that we have not yet confirmed planets there is not a failure. It is a frontier, still being explored by the best instruments available. Chapter 4, Barnard's Star, the fastest moving star in the sky. Distance from Earth, 5.9578 light-years, 1.8281 parsecs. Constellation, Ophiuchus star, type, red dwarf, M4.0VE. The fourth nearest star to the Sun is Barnard's star, located in the constellation Ophiuchus at a distance of about 5.96 light-years. It is invisible to the naked eye, far too dim, but has the largest proper motion of any star in the sky. It moves across the sky at approximately 10.36 arcseconds per year, which means it covers a distance equal to the apparent diameter of the full moon every 180 years. For a star, this is extraordinary. Most stars have proper motions measured in tiny fractions of an arcsecond per year. Barnard's star's rapid apparent motion across the sky is a direct consequence of its proximity. Nearby stars appear to move faster against the background of more distant stars, for the same reason that a nearby car on a highway appears to move faster than a distant one. Barnard's star was identified by the American astronomer E. Barnard in 1916, who noticed its rapid motion when comparing photographic plates taken years apart. It is sometimes called Barnard's runaway star for this reason, though runaway is slightly misleading. It is not moving unusually fast through space, it just appears to move unusually fast across the sky because it is close. Barnard's star is a red dwarf, somewhat larger and brighter than Proxima Centauri, but still very dim by solar standards. Its mass is approximately 0.144 solar masses, its radius approximately 0.196 solar radii, and its surface temperature approximately 3,134 Kelvin. Its luminosity is about 0.00355 solar luminosities. It emits about 1/3% of the Sun's total energy output. It is not a flare star in the same class as Proxima. It is somewhat older and less magnetically active, though it has been observed to produce flares. Barnard's star is also one of the most studied stars in the solar neighborhood, precisely because it is the nearest single star to the Sun. Alpha Centauri is a triple system, so Barnard's holds the distinction of being the nearest solitary stellar object. This makes it a particularly attractive target for radial velocity planet searches, since the signal from an orbiting planet is not complicated by the gravitational influence of a stellar companion. Its high proper motion also makes it valuable for tests of stellar kinematics and the dynamics of the local stellar population. By tracking its motion carefully over decades, astronomers can determine its three-dimensional velocity through space with extraordinary precision. What makes Barnard's star particularly interesting from a historical perspective is its role in one of the great false alarms of exoplanet science. In the 1960s and 1970s, the Dutch-American astronomer Peter van de Kamp published a series of papers claiming to have detected the gravitational wobble of Barnard's star caused by one or two large orbiting planets. Van de Kamp's measurements, based on decades of photographic plates taken at the Sproul Observatory, appeared to show a systematic oscillation in the star's position consistent with a Jupiter-mass planet. This was enormously exciting. It seemed to be direct evidence for planets around the nearest single star to the Sun. Alpha Centauri is a binary. Proxima had not yet been confirmed to have planets. The Van de Kamp planets were discussed in astronomical literature for decades. The problem revealed gradually through the 1970s and 1980s, was that the oscillation Van de Kamp detected was an artifact of changes to the telescope's optics, a lens replacement that had introduced a systematic error in the photographic plates. When this was accounted for, the planetary signal disappeared. The Van de Kamp planets did not exist. It was one of the most instructive episodes in the history of exoplanet research. A cautionary tale about systematic errors and confirmation bias that shaped the methodological standards for the eventual confirmed detections of the 1990s and beyond. Modern searches using radial velocity and astrometric methods far more precise than Van de Kamp's photographic plates have been conducted for Barnard's star in recent years. In 2018, a team led by Ignasi Ribas of the Institute of Space Sciences in Barcelona announced the detection of a planet candidate, Barnard's star B, using combined radial velocity data from multiple spectrographs. The candidate has a mass of at least 3.2 Earth masses, classifying it as a super-Earth or mini-Neptune in an orbit of 232.8 days at a distance of 0.404 astronomical units. At this distance from such a faint star, Barnard's star B would receive only about 2% of the energy Earth receives from the Sun, placing it far outside the habitable zone and making it extremely cold, with surface temperatures estimated below minus 150 degrees Celsius, even if it has a thick atmosphere. Barnard's star B is not a habitable zone planet. However, the status of this detection is uncertain. Subsequent analyses of the data by other teams have raised concerns about whether the 232.8-day signal is produced by stellar activity rather than by an orbiting planet. Red dwarf stars can produce periodic signals in radial velocity data from star-spot activity, dark or bright regions rotating with the star, that can mimic the signal of an orbiting planet. The debate over Barnard's star B's existence continues in the literature, and it has not been confirmed to the standard of certainty required for a firm detection. Despite the uncertainty about its planets, Barnard's star is notable for one additional distinction. It is the star that has approached the Sun most recently in historical astronomical terms, and that is currently approaching us. Barnard's star is closing in on the solar system at a radial velocity of approximately 110 kilometers per second. It is moving toward us. In approximately 9,700 years, Barnard's star will reach its closest approach to the Sun at a distance of about 3.75 light years, making it briefly the nearest star to the Sun, displacing even Proxima Centauri. After that closest approach, it will recede. The current nearest star hierarchy is not permanent. The stellar neighborhood is in constant motion. Chapter 5. Wolf 359. One of the faintest stars near the Sun, distance from Earth, 7.7825 light years, 2.3853 parsecs. Constellation, Leo star, type, red dwarf, M6.5, VE. Wolf 359 is one of the faintest stars in the solar neighborhood, so faint that it has an absolute magnitude of 16.55, meaning that even if placed at the standard reference distance of 10 parsecs, 32.6 light years, it would still be far too dim to see with the naked eye. Its apparent magnitude as seen from Earth is about 13.5. requiring a telescope to see. It sits in the constellation Leo at a distance of approximately 7.78 light-years. Wolf 359 was catalogued by the German astronomer Max Wolf in the early 20th century as part of his systematic survey of stars with high proper motion, the same technique that revealed many of the nearest stars, since nearby stars tend to have larger apparent motions across the sky. It is designated Wolf 359 simply because it was the 359th entry in Wolf's catalog. Physically, Wolf 359 is one of the smallest and least massive stars known to have sufficient mass to sustain hydrogen fusion in its core. Its mass is approximately 0.09 solar masses, its radius approximately 0.144 solar radii, and its surface temperature approximately 2,800 Kelvin, among the coolest surfaces of any true star, as opposed to a brown dwarf which does not sustain true hydrogen fusion. Its luminosity is a mere 0.0014% of the Sun's, about 1/70,000th of the Sun's energy output. Wolf 359 is, by the standards of stellar physics, barely a star at all. It sits just above the hydrogen-burning threshold, below which an object would be a brown dwarf rather than a true star. Despite its obscurity in astronomy, Wolf 359 is probably most familiar to science fiction fans from its appearance in a legendary episode of Star Trek, The Next Generation, in which the Battle of Wolf 359, a devastating engagement between Starfleet and the Borg, takes place at this star. The choice was presumably motivated by Wolf 359's proximity to Earth, making it a plausible nearby battleground. The star itself, were you to visit it, would be an underwhelming destination, a faint red-orange glow, contributing almost no warmth or light at any reasonable distance. The habitable zone of Wolf 359 sits at a distance of only about 0.035 astronomical units, an orbital period of just over 5 days, and any planet there would be tidally locked and subject to intense, frequent flares. It is one of the nearby stars least likely to host a clement environment for life, despite being among the 20 nearest stars to Earth. It is a reminder that proximity is not the same as promise. Wolf 359 is a flare star of significant activity. It produces powerful, frequent flares, sudden brightness increases of up to a factor of several, with associated ultraviolet and X-ray bursts. Any planet in Wolf 359's habitable zone would orbit at an extraordinarily close distance because the star is so faint, and would be subject to this intense flare environment. The combination of extreme proximity to the star and frequent energetic flares makes Wolf 359 one of the less promising nearby stars from a habitability perspective. Chapter 6, Leyland 21185, an ancient neighbor in Ursa Major distance from Earth, 8.2905 light-years, 2.5408 parsecs. Constellation, Ursa Major star, type, red dwarf, M2.0V. Leyland, 21,185, is the nearest star in the northern constellation Ursa Major, located at approximately 8.29 light-years from the Sun. It is a somewhat more substantial red dwarf than Wolf 359, or Proxima, with a mass of about 0.386 solar masses, a radius of about 0.393 solar radii, and a surface temperature of approximately 3,828 Kelvin. Its luminosity is about 0.022 solar luminosities, roughly 2% of the Sun's output. It is invisible to the naked eye with an apparent magnitude of about 7.5, requiring binoculars or a small telescope to detect. The star is named for the French astronomer Jérôme Lalande, who observed it as part of his monumental catalogue of over 47,000 stars in the early 19th century. It has a relatively large proper motion across the sky, another signature of a nearby star. Lalande 21,185 has been the subject of planet searches for decades. In the 1990s, the same astronomer who originally championed Van de Kamp's Barnard's star planets, George Gatewood, claimed to have detected astrometric evidence for 2 planets around Lalande 21,185, based on Hubble Space Telescope observations. These claimed detections did not survive subsequent scrutiny, repeating the pattern of the Barnard's star episode. More recent and more rigorous searches have found more promising results. In 2021, a team using precise radial velocity measurements announced the detection of 2 planet candidates around Lalande 21,185. The inner candidate, Lalande 21,185b, has a minimum mass of about 2.7 Earth masses and orbits at a period of 12.9 days. The outer candidate, Lalande 21,185c, has a minimum mass of about 13 Earth masses, making it a Neptune-class object, and orbits at a period of about 3,000 days. These candidates require further confirmation, but they represent the most plausible current evidence for a planetary system around Lalande 21,185. What makes Lalande 21,185 interesting from a longer perspective is its age. It is estimated to be a very old star, possibly 10 billion years or more in age, more than twice the age of the Sun. If its planets are similarly old and have maintained stable orbits and stable stellar irradiation throughout, they have had an extraordinarily long time to develop whatever chemistry or biology their environments permit. Chapter 7. Sirius, the brightest star in the night sky, and a near neighbor distance from Earth. 8.6 light-years, 2.64 parsecs. Constellation, Canis Major star, types Sirius A 1V, blue-white main sequence, Sirius B, DA2, white dwarf. We have, up to this point, been discussing stars that are invisible or barely visible to the naked eye, dim red dwarfs whose proximity is their only claim to cosmological significance. Now we reach a very different type of star, Sirius, the brightest star in the night sky, and at 8.6 light-years, the 5th nearest stellar system to the Sun. Sirius is brilliant. Its apparent magnitude of -1.46 makes it by far the brightest star visible from Earth, outshining everything in the night sky except the Moon, Venus at its brightest, and very occasionally Jupiter and Mars. Sirius is so bright that it was used as a navigational star for millennia, known to virtually every ancient culture and named in nearly every astronomical tradition. The ancient Egyptians tracked Sirius's heliacal rising, its first appearance above the eastern horizon just before sunrise, as a herald of the annual flooding of the Nile and the beginning of the agricultural year. The star's name comes from the Greek word meaning glowing or scorching, an apt description of its fierce blue-white brilliance. Sirius A, the visible component of what is actually a binary system, is a blue-white main sequence star of spectral type A1V with a mass of approximately 2.06 solar masses, a radius of approximately 1.711 solar radii, and a surface temperature of approximately 9,940 Kelvin, nearly twice the Sun's surface temperature. Its luminosity is approximately 25.4 solar luminosities. It emits 25 times as much energy as the Sun. This combination of relative proximity, 8.6 light-years, and high intrinsic luminosity makes Sirius A appear so brilliant from Earth. Sirius B is one of the most historically significant astronomical objects. It is a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel, shed its outer layers as a planetary nebula, and collapsed to a compact object roughly the size of Earth, but containing about 0.978 solar masses of material. It was the first white dwarf ever discovered. Its existence was predicted by the German-American astronomer Friedrich Bessel in 1844, who noticed a slight wobble in Sirius's path across the sky consistent with an invisible companion. The companion was finally directly observed in 1862 by the American telescope maker Alvan Clark, who spotted the faint companion, then called the Pup, while testing a new lens. Sirius B's visual confirmation was a major triumph of predictive astronomy, confirming that gravitational perturbations could reveal invisible bodies. Sirius B has a mass of approximately 0.978 solar masses, nearly as massive as the Sun, compressed into a radius of only about 0.0084 solar radii, or roughly 5,800 kilometers, slightly smaller than Earth. Its surface temperature is approximately 25,200 Kelvin, hotter than the surface of Sirius A, but because of its tiny size, it emits only about 0.056 solar luminosities. Sirius B was once a star significantly more massive than the Sun, which exhausted its hydrogen fuel, expanded into a red giant or supergiant, shed its outer layers, and left behind this dense remnant. The time required for Sirius B to have evolved through its main sequence life and become a white dwarf constrains the age of the Sirius system to approximately 200 to 300 million years, making it significantly younger than the Sun. The density of Sirius B deserves a moment of attention because it is one of the most extreme properties of any object near Earth. With nearly a solar mass compressed into a volume slightly smaller than Earth, Sirius B has a density of approximately 1 million grams per cubic centimeter, roughly 1 million times denser than water, and about 300,000 times denser than the densest naturally occurring material on Earth. A teaspoonful of Sirius B's material would weigh approximately 5 tons, more than a large SUV. This extraordinary density is what defines white dwarfs as a class. They are supported against gravitational collapse not by nuclear fusion, which has stopped, but by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state. Electron degeneracy pressure does not require any energy source to maintain, which is why white dwarfs can remain stable essentially indefinitely without burning fuel. Sirius B will cool slowly over billions to trillions of years, eventually becoming a cold, dark black dwarf, though no black dwarfs yet exist in the universe, because the cooling timescale exceeds the current age of the cosmos. Sirius A's spectral type, A-type blue-white, places it in a class of stars with limited potential for habitable planets by conventional criteria. Its high surface temperature means it emits strongly in the ultraviolet, which is energetic enough to damage complex organic molecules. Its relatively short main sequence lifetime, A-type stars live for only about 1 to 2 billion years before evolving off the main sequence, leaves limited time for biological evolution compared to the 4.6 billion years Earth has had with the Sun. The presence of a white dwarf companion at a relatively close average separation, currently about 20 astronomical units, though the orbit is highly eccentric, ranging from 8 to 32 astronomical units, further complicates the dynamical environment for any hypothetical planets. No planets have been confirmed around Sirius A, and the system is not generally considered a strong candidate for habitable worlds. Nevertheless, Sirius holds a unique cultural significance that no other nearby star can match. It is the star that most humans throughout most of human history have looked up at and wondered about. Its brilliance made it unavoidable. It dominated the winter sky of the northern hemisphere and the summer sky of the southern hemisphere. It served as a navigational anchor for sailors and travelers. It anchored the calendars of agricultural civilizations. It was worshipped as a deity in several traditions and celebrated in poetry and myth across dozens of cultures. The fact that this most culturally significant of all night sky stars is also genuinely one of the nearest stars to Earth is a pleasing coincidence. For once, the most visible and the most proximate align. Chapter 8, Luyten 726-8, a flaring binary red dwarf distance from Earth, 8.7280 light-years, 2.6743 parsecs. Constellation, Cetus star, type, both M5.5, VE and M6.0. VE red dwarfs. At a distance of approximately 8.73 light-years lies a binary system of 2 red dwarf stars. Luyten 726-8a, also designated UV Ceti A, and Luyten 726-8b, UV Ceti B. Located in the constellation Satis, this is another system that is invisible to the naked eye, requiring a telescope to observe. The 2 red dwarfs orbit each other at an average separation of about 5.4 astronomical units, with an orbital period of approximately 26.5 years. Both stars are of spectral type, M5 to M6, cool, faint, and red, with masses of about 0.102 and 0.100 solar masses respectively, and radii of about 0.162 and 0.159 solar radii. Their surface temperatures are both approximately 2,650 to 2,700 Kelvin. Luyten 726-8 is most famous in astronomical literature, not for its proximity, but for its extreme flare activity. UV Ceti B, in particular, is the prototype of the class of flare stars known as UV Ceti variables, stars that produce sudden, dramatic increases in brightness, flares, caused by magnetic reconnection events on the stellar surface. UV Ceti B has been observed to brighten by as much as 75 times its normal luminosity during major flare events. with the brightening occurring over seconds to minutes. The flares emit intense radiation across the electromagnetic spectrum, with particularly strong emission in the ultraviolet and X-ray bands. UV Ceti variables are now known to be a common class of phenomenon among M-dwarf stars. Essentially, all M-dwarfs flare to some degree, with the most magnetically active ones producing the most extreme events. UV Ceti gives its name to the entire class because it was one of the first and most dramatic examples observed. No confirmed planets have been detected around either component of the Luyten 726-8 system, and the intense flare activity of both stars makes it a challenging environment for habitable zone planets, even if they exist. The habitable zones of these very faint stars are at very short orbital periods, and any planet in the habitable zone would be subject to the same ultraviolet and X-ray bombardment that characterizes Proxima Centauri b's situation, but potentially more extreme, given UV Ceti's exceptional flare activity. Chapter 9. Ross 154, a young and violent red dwarf distance from Earth, 9.6813 light years, 2.9675 parsecs. Constellation: Sagittarius star type, red dwarf, M3.5 VE. At approximately 9.68 light years from the Sun, Ross 154 is the nearest star in the constellation Sagittarius, the direction toward the center of the Milky Way. It was catalogued by Frank Elmore Ross in 1926, who compiled an extensive list of stars with high proper motion during his work at the Yerkes Observatory. Like most of its neighbors in this survey, it is far too faint to see with the naked eye, with an apparent magnitude of about 10.4, requiring a decent amateur telescope to observe even as a dim point of reddish light. Ross 154 is an M3.5 flare star, active, magnetically energetic, and considerably younger than most of its neighbors in the solar vicinity. Its estimated age is only about 1 billion years, making it a relative youngster compared to the Sun's 4.6 billion years, and considerably younger than Barnard's star, or Lalande, 21,185. Young M-dwarfs are characteristically more magnetically active than older ones. As stars age, they spin more slowly, losing angular momentum to their magnetized stellar winds. And slower rotation is associated with weaker magnetic dynamos, and therefore fewer and less intense flares. Ross 154 is in an energetically volatile phase of its stellar life, producing frequent ultraviolet and X-ray flares. Its physical properties are those of a middling M-dwarf. Mass approximately 0.17 solar masses, radius approximately 0.24 solar radii, surface temperature approximately 3,340 Kelvin, and luminosity approximately 0.0038 solar luminosities, about 1/3% of the Sun's output. Its habitable zone sits at roughly 0.075 astronomical units, implying an orbital period of about 6 days for a planet receiving Earth-equivalent stellar flux. Any planet in Ross 154's habitable zone would be tidally locked and subject to intense flare radiation, particularly given the star's youth. As it ages and slows its rotation, the flare activity will diminish over billions of years. By the time it reaches the Sun's current age, it will be a considerably quieter star. But for now, It is one of the more challenging stellar environments among the nearest stars. No confirmed planets have been detected around Ross 154 with current instrumentation. Its relative youth and flare activity make precision radial velocity measurements more difficult. Stellar activity introduces noise into the radial velocity signal that can mask or mimic planetary signals. As new spectral analysis techniques are developed to separate stellar activity signatures from planetary signals, stars like Ross 154 will become more tractable targets. Chapter 10. Ross 248. The star that will one day be our nearest neighbor. Distance from Earth 10.322 light years, 3.1624 parsecs. Constellation Andromeda star, type red dwarf, M5.5 VE. Ross 248 sits at approximately 10.32 light years from Earth in the constellation Andromeda, making it the nearest star in that constellation. It was catalogued by Frank Elmore Ross in 1926, the same year he catalogued Ross 154. Like most of the stars in this survey, it is invisible to the naked eye, with an apparent magnitude of about 12.3, requiring a telescope for observation. Ross 248 is a small, faint M5.5 red dwarf with a mass of approximately 0.136 solar masses, a radius of approximately 0.178 solar radii, a surface temperature of approximately 3054 Kelvin, and a luminosity of approximately 0.00185 solar luminosities, a little less than 0.1% of the Sun's output. It is a flare star, though not as intensely active as some of its counterparts at similar spectral types. Its estimated age is uncertain, but probably several billion years, making it older and somewhat less active than Ross 154. What makes Ross 248 genuinely special is not its current position in our stellar neighborhood, but its trajectory through space. Ross 248 is approaching the solar system. Its radial velocity, the component of its motion directly toward or away from us, is about -81 kilometers per second, meaning it is closing the gap between itself and the Sun at 81 kilometers every second. In approximately 33,000 years from now, Ross 248 will pass within about 3.024 light years of the Sun, closer than Proxima Centauri's current distance of 4.24 light years, making it the nearest star to the Sun for a period of several thousand years before it recedes again. Ross 248's brief tenure as our nearest stellar neighbor lies in the geologically recent future. People who will be alive in 33,000 years, if humanity survives, will live during the era of Ross 248 as the nearest star. This is worth sitting with for a moment. The identity of the nearest star to Earth is not fixed. It is a slowly changing fact, determined by the relative motions of the stars through the Milky Way. Proxima Centauri is our nearest neighbor right now. Barnard's star will make its closest approach in about 9,700 years. Ross 248 will take the nearest star title in about 33,000 years. And farther in the future, as the stars continue their slow drifts, other configurations will emerge. The cosmic neighborhood is in constant, slow rearrangement. a stellar ballet, operating on timescales of thousands to tens of thousands of years, imperceptible in a human lifetime, but substantial over the span of civilizations. Voyager 2, the second of the two Voyager spacecraft launched in 1977, is currently headed roughly in the direction of Ross 248, though not targeted at it. In approximately 40,000 years, Voyager 2 will pass within about 1.7 light-years of the star. Not close enough to enter any planetary system, but a remarkable footnote to the fact that humanity's most distant envoys will, over cosmic timescales, drift through the solar neighborhood and come within measurable proximity of several of its stars. No confirmed planets have been found around Ross 248, and the star has not been as intensively searched as some of the other nearby stars. It remains an understudied object despite its proximity and its intriguing future as our nearest stellar neighbor. Chapter 11, Epsilon Eridani, the nearest sun-like star, with a confirmed planetary system. Distance from Earth, 10.522 light-years, 3.2216 parsecs. Constellation, Eridanus star. Type, orange dwarf, K2V. At 10.52 light-years from Earth, Epsilon Eridani is one of the most extensively studied stars in the solar neighborhood, and for good reason. It is the nearest single star to the Sun that is both similar enough to our own star to be considered sun-like in character and confirmed to have a planetary system. It sits in the southern constellation Eridanus, and unlike most of the stars we have discussed, it is actually visible to the naked eye with an apparent magnitude of about 3.7. A modestly bright star, unremarkable among the thousands of stars you can see on a clear night, but perfectly visible without optical aid. Epsilon Eridani is a K2V star, a K-type main sequence star, often called an orange dwarf, slightly cooler and less luminous than the Sun. Its mass is approximately 0.82 solar masses. Its radius approximately 0.735 solar radii, and its surface temperature approximately 5,084 Kelvin. Its luminosity is approximately 0.34 solar luminosities, about a third of the Sun's energy output. This means Epsilon Eridani's habitable zone sits somewhat closer to the star than Earth's orbit around the Sun, approximately 0.5 to 0.6 astronomical units, where a planet would receive Earth-equivalent stellar flux. What makes Epsilon Eridani's spectral type, K2, interesting in the context of habitability is the same property we noted for Alpha Centauri b. K-type stars occupy a compelling middle ground between the Sun and red dwarfs. They are cooler than the Sun, but not dramatically so, meaning their habitable zones are at orbital periods of a few months rather than a few days, reducing the problem of tidal locking. They are less energetically violent than M dwarfs, producing fewer and less intense stellar flares. And they live longer than the Sun. A K-dwarf of Epsilon Eridani's mass has a main sequence lifetime of roughly 15 to 20 billion years, compared to the Sun's 10 billion years. Any life that developed on a K-dwarf planet would have 50 to 100% more time available to evolve complex forms than life on Earth has had. However, Epsilon Eridani is young, very young by stellar standards. Its estimated age is only about 400 to 800 million years, depending on which age dating method is used. For context, Earth was 400 to 800 million years old during the period known as the Late Heavy Bombardment, a phase of intense asteroid and comet impacts that reshaped the inner solar system and may have both threatened and seeded early life. Any planets around Epsilon Eridani are at a comparable evolutionary stage. If they exist, they are geologically young, probably still being heavily bombarded, and not yet settled into the stable, long-term configuration that Earth achieved by about 3.8 billion years ago. Life, if it has begun on a planet of Epsilon Eridani, is at best in its very earliest stages. More probably, the environment is still too violent for life as we know it to gain a stable foothold. Epsilon Eridani is the nearest sun-like star, but it is showing us the solar neighborhood as it was in our own early history, not as it is today. The confirmed component of Epsilon Eridani's planetary system is Epsilon Eridani b, a giant planet first announced in 2000 using the radial velocity method by William Cochrane, Artie Hatzes, and colleagues at the University of Texas. The detection generated considerable excitement as one of the first nearby star planet detections. Epsilon Eridani b has a minimum mass of approximately 0.78 Jupiter masses. It is a gas giant, OE Jupiter analog, in an eccentric orbit with a period of approximately 7.4 years at an average distance of about 3.4 astronomical units. This is well outside the habitable zone of Epsilon Eridani. The planet's existence was initially questioned. The star's youth means it is active, introducing noise into radial velocity data. But subsequent observations over 2 decades have confirmed the orbital signal, and Epsilon Eridani b is now considered a well-established detection. Beyond the confirmed planet, Epsilon Eridani has a rich disk structure. It possesses a prominent debris disk, a disk of dust and larger rocky bodies produced by ongoing collisions between planetesimals, analogous to the asteroid belt and Kuiper belt of our solar system, but substantially more massive, reflecting the system's youth and ongoing dynamical activity. The debris disk has been imaged by infrared telescopes, particularly the Spitzer Space Telescope and the James Clerk Maxwell Telescope, and shows a complex structure with inner and outer components suggesting the presence of additional planets sculpting the disk. The inner warm dust belt and the outer cold disk ring, at about 60 astronomical units, are both consistent with a solar system-like architecture in which planets at intermediate distances are clearing gaps in the debris. Searches for additional planets using direct imaging have not confirmed any, but the debris disk's structure suggests they are there, waiting for instruments of sufficient sensitivity and contrast to reveal them. The James Webb Space Telescope's mid-infrared capabilities have been applied to Epsilon Eridani, and future extremely large ground-based telescopes with high-contrast imaging instruments may be able to directly image planets in this system. It is worth pausing here on what Epsilon Eridani's youth means in a broader sense. The star system is about 400 to 800 million years old, the same age range as Earth during what geologists call the Hadean and early Archean eons. During that period on Earth, the surface was being repeatedly sterilized by large asteroid impacts. The Moon had formed only recently from the giant impact with the proto-Earth. Oceans were just beginning to stabilize, and the first tentative chemistry of life may or may not have been experimenting with self-replication in warm, mineral-rich water. If there is any analogy between the early Earth and any world around Epsilon Eridani, the analogy is to this pre-biotic, chaotic early stage, not to the settled, biosphere-rich Earth of today. What Epsilon Eridani is showing us, therefore, is not a twin of the current solar system, but a time machine, a window into what our own neighborhood looked like when the solar system was in its infancy. Studying Epsilon Eridani with the best available instruments is, in a very real sense, studying our own past projected onto a nearby star. Epsilon Eridani's cultural significance rivals that of Alpha Centauri among nearby stars. It appears in Isaac Asimov's Foundation universe, in various Star Trek references, and most explicitly in the television series Babylon 5, which sets its titular space station in the Epsilon Eridani system, a choice that reflects the system's combination of proximity to Earth and genuine scientific interest. The choice is not arbitrary. Epsilon Eridani is, in a real sense, one of the most interesting stars within 15 light years. The nearest visible to the naked eye star with a confirmed planetary system, the nearest K-dwarf in the immediate neighborhood, and a star young enough to show us what our own system looked like several billion years ago. Chapter 12, Lechail 9352. The nearest star in Pisces Austrinus distance from Earth, 10.742 light years, 3.2930 parsecs. Constellation, Pisces Austrinus star, type, red dwarf, M1.5 VE. Lechail 9352 sits at approximately 10.74 light years from Earth in the southern constellation Pisces Austrinus, not far in apparent position from the bright star Fomalhaut. It was catalogued by the 18th century French astronomer Nicolas Louis de Lechail during his landmark survey of the southern sky from the Cape of Good Hope between 1751 and 1752, one of the most important early systematic catalogues of southern hemisphere stars. At apparent magnitude 7.3, Lechail 9352 is on the edge of naked eye visibility, just beyond the limit under excellent dark sky conditions, easily visible with binoculars. It is a relatively substantial red dwarf at M1.5. The M1.5 classification places it on the warmer, more massive end of the M dwarf sequence, making it considerably more luminous than the cooler M5 and M6 stars we have discussed. Its mass is approximately 0.489 solar masses, its radius approximately 0.476 solar radii, and its surface temperature approximately 3,626 Kelvin. Its luminosity is approximately 0.024 solar luminosities, about 2.4% of the sun's output. Its habitable zone falls at roughly 0.15 astronomical units, implying orbital periods of about 3 to 4 weeks. Lechail 9352 has an interesting planetary history in the literature. In 2022, a team of astronomers announced the detection of 2 planet candidates using the HARPS spectrograph at the European Southern Observatory's La Silla facility in Chile. The inner candidate has a minimum mass of about 8.7 Earth masses and orbits at a period of 8.7 days, placing it very close to the star and well inside the habitable zone. The outer candidate has a minimum mass of about 14 Earth masses and orbits at a period of about 88 days, also within or near the habitable zone for such a faint star. Both are in the super-Earth to Neptune mass range. These detections are recent and require independent confirmation, but they add Lacaille 9352 to the growing list of nearby red dwarf systems with detected planetary companions. What Lacaille 9352 demonstrates, alongside its near neighbors in this survey, is that planet formation around M dwarfs appears to be common. Nearly every nearby red dwarf that has been searched with sufficient precision and duration has produced planet candidates, and the statistical inference from these detections is that the majority of M dwarfs host planetary systems. Given that M dwarfs constitute 70 to 75% of all stars in the galaxy, this implies that the galaxy is populated with an extraordinary number of planetary systems, far more than would be implied by the planet occurrence rates around Sun-like stars alone. Chapter 13, Ross 128, the nearest quiet red dwarf, with a confirmed planet distance from Earth, 10.919 light-years, 3.3473 parsecs. Constellation, Virgo star. Type, red dwarf, M4.0 VE. Ross 128 is located approximately 10.92 light-years from Earth in the constellation Virgo, catalogued like Ross 154 and Ross 248 by Frank Elmore Ross in his 1926 Proper Motion Survey. At apparent magnitude 11.1, it requires a telescope to see. Its physical properties are those of a typical middle-of-the-road M dwarf. Mass approximately 0.168 solar masses, radius approximately 0.197 solar radii, surface temperature approximately 3,192 Kelvin, and luminosity approximately 0.00362 solar luminosities. It is approaching the Sun at about 31 kilometers per second, and in approximately 71,000 years, it will make its closest approach, coming within about 1.9 light-years of the Sun, briefly making it the nearest star to Earth before it recedes. What elevates Ross 128 above its very similar neighbor, Ross 154, is one key property. It is unusually quiet for an M dwarf of its age and type. Ross 128 shows relatively low levels of magnetic activity and flare production compared to most M dwarfs. It is not a flare star in the UV SETI sense. This relative quiescence makes it a particularly attractive star from a habitability perspective, because the flare environment is one of the most significant challenges for life around M dwarfs. In 2017, a planet was confirmed around Ross 128 using HARPS radial velocity data. Ross 128b has a minimum mass of approximately 1.35 Earth masses, making it a slightly super-Earth-sized world at minimum, and orbits Ross 128 at a period of 9.9 days, at a distance of approximately 0.0496 astronomical units. Given the faintness of the star, this close orbital distance places Ross 128b right in the habitable zone. It receives approximately 1.38 times Earth's solar flux, which is within the range where liquid water could exist on the surface under a wide variety of atmospheric conditions. Ross 128b is one of the best candidates for habitability among confirmed nearby exoplanets, for a combination of reasons. First, it is Earth-like in mass, minimum mass at least. Second, it orbits in the habitable zone. Third, it orbits a quiet star that does not bombard it with intense flares the way Proxima Centauri bombards Proxima b. Fourth, at 10.92 light-years, it is close enough to be one of the most studied targets of future atmospheric characterization missions. Its title: Locking status is uncertain. At 9.9-day orbital period, models suggest it is likely but not absolutely certain to be tidally locked, depending on the planet's internal structure and rotational history. The discovery of Ross 128b in 2017 came alongside an intriguing and ultimately explained mystery. In May 2017, the Arecibo radio telescope detected a series of unusual radio signals coming from the direction of Ross 128. Signals that briefly generated speculation about artificial origin. The signals were ultimately identified as interference from geostationary satellites, whose frequencies overlapped with the frequency range being monitored. The Ross 128 signal is now considered a definitively explained case of radio frequency interference, not extraterrestrial communication. But the episode illustrates the heightened attention that nearby stars with potentially habitable planets attract from SETI researchers monitoring for anomalous signals. Chapter 14, E-Zeu Aquarii, a triple, red dwarf system. Distance from Earth, 11.266 light-years, 3.4533 parsecs. Constellation, Aquarius star. Type, 3 red dwarfs, M5VE plus M5VE plus M. Izid Aquarii, also designated Luyten 789-6, is a triple star system at approximately 11.27 light-years in the constellation Aquarius. All 3 components are dim M-dwarf stars, making this the most extreme multiple star system among the very nearest stars. 2 of the components, Izid Aquarii A and B, orbit each other at a very close separation, while the third, Ez Aquarii C, orbits the close pair at a wider distance. The primary component, Ez Aquarii A, has a mass of approximately 0.11 solar masses, a radius of approximately 0.163 solar radii, and a surface temperature of approximately 2,900 Kelvin. The B and C components are similarly small and faint. All 3 are flare stars. M-dwarfs of this spectral type, at active phases of their evolution, produce frequent energetic flares. The complex gravitational environment of a triple system, with such close orbital separations, severely limits the stable regions for planetary orbits, and no planets have been confirmed in this system. Ez Aquarii demonstrates an important aspect of the solar neighborhood census. Multiple star systems are common. Of the roughly 20 nearest stellar systems within about 13 light-years of the Sun, more than a third are binary or triple systems. The Sun is, in this respect, atypical. The majority of nearby systems consist of 2 or more gravitationally bound stars. The effects of stellar multiplicity on planet formation and habitability are complex. Very close binary pairs, separated by less than about 0.2 astronomical units, can still host circumbinary planets in orbits around both stars, as confirmed by Kepler observations of systems like Kepler 16b, which orbits a binary pair. But the dynamical environment is more chaotic, and the parameter space for stable orbits is more restricted. Chapter 15, Procyon, the bright nearby star with a hidden white Dwarf distance from Earth, 11.402 light-years, 3.4955 parsecs. Constellation, Canis Minor star type, Procyon A, F5425, yellow-white subgiant. Procyon B, DQZ, white dwarf. Procyon is the 8th brightest star in the night sky, with an apparent magnitude of 0.34. It is easily visible from most locations on Earth and has been known, named, and navigated by since antiquity. The name comes from the Greek for before the dog, referring to the fact that it rises before Sirius, the dog star, in the northern hemisphere. It is the brightest star in the small constellation Canis Minor and one of the stars of the Winter Triangle asterism, along with Sirius and Betelgeuse, in the northern winter sky. At 11.40 light-years, Procyon is very close, the 7th nearest stellar system to the Sun. Like Sirius, it is a binary system, Procyon A and the white dwarf, Procyon B. Procyon A is classified as F5425. The F5 indicating it is a yellow-white star somewhat hotter than the Sun, and the 425 indicating it is transitioning between main sequence and subgiant status. It is, in other words, a star beginning to evolve off the main sequence as it exhausts its core hydrogen fuel. Its mass is approximately 1.499 solar masses, its radius approximately 2.048 solar radii, and its surface temperature approximately 6,530 Kelvin. Its luminosity is approximately 6.93 solar luminosities, nearly 7 times the Sun's output, a consequence of both its greater mass and its puffed-up subgiant structure. Procyon A is estimated to be about 1.87 billion years old, significantly younger than the Sun, and will eventually evolve further into a red giant and then leave behind a white dwarf, as Sirius B's progenitor star did. The slight swelling of Procyon A into a subgiant means that its habitable zone has shifted outward from where it was earlier in the star's life. Any planet that might have been in the habitable zone during Procyon A's early main sequence phase has been subjected to increasing luminosity over time. The star's evolution toward a red giant will eventually make the inner solar system of any planet uncomfortably, then fatally, hot. Procyon B is a white dwarf of spectral type DQZ, indicating a carbon and metal polluted white dwarf atmosphere. A white dwarf that has accreted material from orbiting rocky debris, contaminating its otherwise pure hydrogen or helium atmosphere with heavier elements. Its mass is approximately 0.602 solar masses, making it less massive than Sirius B, and its radius is approximately 0.01234 solar radii. It orbits Procyon A at an average separation of about 15 astronomical units, with a period of about 40.8 years. Procyon B was discovered in 1896 by the German-American astronomer John Martin Schaeberle, again through its gravitational influence on Procyon A's proper motion. The same method that revealed Sirius B's existence. No confirmed planets have been detected around Procyon A or B, and given Procyon A's evolutionary stage and the presence of a white dwarf companion, the system is not generally considered a strong habitability candidate. But as one of the nearest bright stars to Earth, Procyon has attracted the attention of SETI researchers monitoring the stellar neighborhood, and it remains a well-studied object in the Solar Neighborhood Census. Chapter 16, 61 Cygni. the first star to have its distance, measured distance from Earth, 11.403 light-years, 3.4956 parsecs. Constellation, Cygnus star. Types, K5V and K7V, two orange dwarfs. 61. Cygni holds one of the most important historical distinctions of any star in the sky. It was the first star, other than the Sun, to have its distance directly and accurately measured. In 1838, the German-Russian astronomer Friedrich Wilhelm Bessel used the stellar parallax method, measuring the apparent shift in 61 Cygni's position against background stars over the course of a year, and determined that it was approximately 10.4 light-years away, a figure remarkably close to the modern measurement of 11.4 light-years, given the instruments available in 1838. This measurement was a landmark in the history of astronomy, confirming for the first time that the stars are genuinely at stellar distances, not a few thousand kilometers as some earlier models had proposed, but incomprehensibly far by any human standard. It established the scale of the stellar neighborhood in a way that no previous measurement had done. The magnitude of what Bessel achieved in 1838 is worth dwelling on. He was working with the 6.2-inch Fraunhofer heliometer at the Königsberg Observatory, a precision instrument for measuring angular separations, but one that required extraordinarily careful work to yield arc-second level precision. The parallax angle he measured for 61 Cygni was 0.3136 arcseconds, a quantity smaller than 1,000th of a degree. Getting this right required 18 months of systematic observations, careful calibration against background reference stars, and rigorous mathematical reduction of the data. When Bessel published his result, it caused a sensation among astronomers, not just because it measured a stellar distance, but because the distance it measured was staggeringly large. Roughly 100 trillion kilometers, a number so far outside ordinary human experience that the word incomprehensible is not hyperbole, but a literal description of the cognitive challenge the number presents. The light year as a unit of measurement was essentially invented in response to this result, because kilometers and astronomical units were inadequate to express the distance without producing unwieldy strings of digits. Bessel's measurement of 61 Cygni was the moment at which humanity first empirically confronted the true scale of interstellar space. Bessel chose 61 Cygni specifically because of its exceptionally large proper motion. It moves about 5.28 arcseconds per year across the sky, one of the largest proper motions of any naked eye star, earning it the nickname the Flying Star among 18th century astronomers. William Piazzi first noted its large proper motion in 1804. The large proper motion was correctly interpreted as a sign of proximity, making it a natural first target for the parallax measurement. 61 Cygni is a binary system of two K-type orange dwarf stars, 61 Cygni A, K5V, and 61 Cygni B, K7V, orbiting each other with a period of approximately 659 years at an average separation of about 84 astronomical units. Both stars are cooler, less massive, and less luminous than the Sun. 61 Cygni A has a mass of approximately 0.708 solar masses, a radius of approximately 0.665 solar radii, a surface temperature of approximately 4,374 Kelvin, and a luminosity of approximately 0.153 solar luminosities. 61. Cygni b is slightly smaller and cooler, mass approximately 0.663 solar masses, radius approximately 0.595 solar radii, temperature approximately 4,044 Kelvin, luminosity approximately 0.085 solar luminosities. Both stars are old, estimated at about 6 billion years, and relatively magnetically inactive for K-dwarfs, producing modest flare activity. They are, from a habitability standpoint, among the more interesting stars in the solar neighborhood. The wide binary separation of 84 astronomical units on average means that planetary orbits within a few astronomical units of either star are dynamically stable. The gravitational influence of the companion star at such a large separation is relatively modest. 61 Cygni is the system where van de Kamp's infamous false detection story almost repeated itself. Van de Kamp, after his retracted Barnard's star-planet claim, later claimed to have detected astrometric evidence for a planet around 61 Cygni. This claim also did not survive subsequent analysis. However, more recent radial velocity searches have found hints of possible planet candidates that remain under investigation. The system is also historically notable because it was an early target of SETI-related searches, beginning with Frank Drake's Project Ozma in 1960, the first systematic search for radio signals from nearby sun-like stars. Project Ozma monitored both 61 Cygni and Epsilon Eridani for artificial radio signals, finding none. It established the template for all subsequent SETI observations and marked the beginning of the scientific era of the search for extraterrestrial intelligence. Chapter 17, Struve 2398, a quiet binary. Red dwarf distance from Earth, 11.525 light-years, 3.5325 parsecs. Constellation, Draco star. Type, 2 red dwarfs, M3.0V and M3.5V. Struve 2398 is a binary system of 2 red dwarfs in the constellation Draco at approximately 11.53 light-years from the Sun. Its 2 components, Struve 2398A and B, have masses of approximately 0.36 and 0.30 solar masses, respectively, with surface temperatures of about 3,441 and 3,313 Kelvin. They orbit each other with a period of roughly 300 years at a separation of about 56 astronomical units. Both components are relatively quiet M-dwarfs, not intensely flaring, making them potentially more hospitable hosts for planets than their more active counterparts. The system was measured and documented by the German-Russian astronomer Friedrich Georg Wilhelm von Struve in the 19th century as part of his monumental Pulkovo catalogue of double stars, one of the foundational works of stellar astronomy. The 2398 designation refers to its position in that catalogue. No confirmed planets have been found around either component, but the system has not been subjected to the most intense radial velocity monitoring campaigns. The 2 K-type adjacent M-dwarfs of Struve 2398 are relatively sun-like in some respects, more massive and warmer than the extreme M-dwarfs like Proxima. and their habitable zones sit at somewhat larger orbital distances than the faintest M dwarfs, reducing the severity of tidal locking for habitable zone planets. Chapter 18, Groombridge 34, another binary red. Dwarf system distance from Earth, 11.624 light-years, 3.5627 parsecs. Constellation, Andromeda star, type, 2 red dwarfs, M1.5V and M3.5V. Groombridge 34 is a binary red dwarf system at approximately 11.62 light-years in the constellation Andromeda, named for the English astronomer Stephen Groombridge, who catalogued it in his Catalogue of Circumpolar Stars, published posthumously in 1838. The same year, Bessel measured the distance to 61 Cygni. The primary component, Groombridge 34A, is a relatively substantial M1.5 red dwarf, with a mass of approximately 0.38 solar masses, a radius of approximately 0.38 solar radii, and a surface temperature of approximately 3,703 Kelvin. Its companion, Groombridge 34b, is a smaller M3.5 dwarf with a mass of about 0.16 solar masses. They orbit each other at an average separation of about 147 astronomical units, with a long orbital period measured in centuries. Groombridge 34A is a flare star, designated GX Andromedae as a variable star, and produces occasional energetic flares. Groombridge 34b, designated GQ Andromeda, is also a flare star, sometimes producing dramatic brightness increases. Despite the wide binary separation, the flare environments of both stars present challenges for potential habitable zone planets. In 2014, a planet candidate was announced around Groombridge 34A, a super-Earth with a mass of approximately 5.35 Earth masses in a roughly 11.4-day orbit, well inside the star's habitable zone. This detection remains a candidate rather than a fully confirmed planet, pending independent verification. If confirmed, it would add Groombridge 34A to the growing list of nearby M dwarfs with compact planetary systems. Chapter 19, Epsilon Indi, a K dwarf with a brown dwarf. Binary companion, distance from Earth, 11.824 light-years, 3.6241 parsecs. Constellation, Indus star, type, Epsilon Indi, A, K4V, orange dwarf, Epsilon Indi BA and BB, brown dwarfs. Epsilon Indi is a fascinating triple system atoll, approximately 11.82 light-years in the southern constellation Indus, one of the few constellations that represents a modern geographic concept rather than a mythological figure. It consists of a K-type orange dwarf primary, Epsilon Indi A, and a widely separated pair of brown dwarfs, Epsilon Indi BA and BB, which orbit the primary at a very large distance of approximately 1,500 astronomical units. Epsilon Indi A is one of the more appealing stars in the solar neighborhood from a habitability perspective. It has a mass of approximately 0.762 solar masses, a radius of approximately 0.732 solar radii, and a surface temperature of approximately 4,280 Kelvin. Its luminosity is approximately 0.22 solar luminosities, and it is an old star, estimated at about 3.7 to 5.7 billion years. comparable to the Sun's age of 4.6 billion years. Its habitable zone falls at approximately 0.5 astronomical units. It is a K-dwarf like Alpha Centauri b and 61 Cygni, in the class of stars considered by some astrobiologists to be optimal for habitable planets, offering stability and longevity without the extremes of M-dwarf flare activity. In 2022, a major discovery was announced around Epsilon Indi A. Using a combination of radial velocity data collected over many years at multiple observatories, a team led by Fabo Feng reported the detection of a cold giant planet, Epsilon Indi AB, with a mass of approximately 3 Jupiter masses in a relatively wide orbit. The planet's existence was subsequently confirmed, and its orbit refined through direct imaging. In 2023, James Webb Space Telescope observations directly imaged Epsilon Indi AB in the mid-infrared, making it one of the first exoplanets to be directly imaged in this wavelength range and providing a direct measurement of its thermal emission. JWST's image of Epsilon Indi AB is a landmark, the first direct image of a cold giant planet orbiting a nearby star at a relatively wide separation, analogous in some ways to imaging Jupiter from the outside of our solar system. The directly imaged planet is a cold giant, much too massive and far from the star to be habitable itself. But its existence tells us something important about the architecture of the Epsilon Indi system. It hosts at least one large planet in a wide orbit, raising the possibility of smaller inner planets yet to be detected. The system's age, stellar type, and now confirmed planetary companion make Epsilon Indi A one of the highest priority targets for future searches for Earth-like planets, using the next generation of direct imaging instruments. The JWST image of Epsilon Indi AB deserves a specific moment of appreciation because what it represents scientifically is deeper than any single data point about one planetary system. For decades, the direct imaging of exoplanets was effectively impossible for cold, distant planets. Only young, hot, self-luminous giant planets at very wide separations could be imaged because they were still warm from their formation and therefore bright in the infrared. Epsilon Indi AB is different. It is an old, cold planet, approximately the temperature of Jupiter, cooled to the point where its atmospheric emission is concentrated in the mid-infrared wavelengths that only JWST can access with sufficient sensitivity from space. The fact that JWST could image it at all represents a step toward the eventual direct imaging of planets at temperatures closer to those of habitable worlds, warm, Earth-like surfaces at temperatures of 250 to 300 Kelvin. Emitting in the mid-infrared at wavelengths, JWST is well suited to observe. Epsilon Indi AB is not the destination of that scientific journey. It is an early waypoint, demonstrating that cold planets at stellar distances can now be directly imaged for the first time. The implication for what comes next, the potential direct imaging of an Earth-like planet around a nearby star in the coming decades, is one of the most exciting prospects in all of contemporary astrophysics. The brown dwarf companions, Epsilon Indi BA and BB, were discovered in 2003 by a team at the European Southern Observatory. They are among the nearest known brown dwarfs to the Sun and the first brown dwarf binary system discovered. Their masses are approximately 47 and 28 Jupiter masses, respectively, too low for hydrogen fusion, but sufficient for deuterium burning in their early histories. They orbit each other at a separation of only about 2.1 astronomical units, far too close for stable planetary orbits between them. The discovery of this brown dwarf binary orbiting so far from Epsilon Indi A, at 1,500 astronomical units, was itself a significant finding. Such wide companion systems were not expected to be stable on long timescales, though the system appears dynamically stable within the age of the universe. Chapter 20. The Sun Itself. What our star looks like from the neighborhood. Before we conclude, it is worth completing the picture by turning the perspective around. We have been describing the nearest stars as seen from Earth, but each of those stars sees us too. They look out across their own interstellar distance, and in the direction of the Sun, they see another star. What does the Sun look like from the perspective of each of these neighboring stars? From Proxima Centauri at 4.24 light-years, the Sun would appear as a star of apparent magnitude approximately 0.4, easily visible to the naked eye, brighter than Sirius appears from Earth, one of the dozen or so brightest stars in that sky. Our Sun would be located in the constellation Cassiopeia as seen from Proxima, adding a sixth bright star to the familiar W shape. Earth itself would be far too faint to detect with the naked eye from Proxima. It would require an extraordinarily powerful telescope to distinguish the tiny planet from the glare of its nearby star. From Sirius, 8.6 light-years away, the Sun would appear as a star of apparent magnitude approximately 1.8. Still, clearly visible to the naked eye, roughly as bright as the star Deneb appears from Earth. From Epsilon Eridani at 10.5 light-years, the Sun would be of magnitude approximately 2.4, a respectable naked-eye star, not among the most brilliant but clearly detectable on any clear night. From the farthest star we have discussed, Epsilon Indi at 11.8 light-years. The Sun would be of magnitude approximately 2.6, comparable to the brightness of Polaris, the North Star, as seen from Earth. From none of these nearby stars, and from no location within the solar neighborhood, would the Sun be the brightest star in the sky. Sirius would be far brighter from almost any nearby vantage point, because Sirius's intrinsic luminosity of 25.4 solar luminosities means it dominates the neighborhood. The Sun is a respectable star, visible, identifiable, and knowable from the nearest stellar systems. But it is not a standout. It is a yellow-white point of modest brilliance in a sky that, from most nearby stars, is dominated by Sirius's brilliant blue-white glare. This perspective is worth holding in mind as we complete the tour of the solar neighborhood. The Sun is not special among the nearby stars in any dramatic way. It is slightly more massive and more luminous than most of its red dwarf neighbors, but it is not exceptional. It is not the brightest, not the most massive, not the most metal-rich, not the oldest, not the youngest. It is an ordinary G-type star of modest distinction, and its nearest neighbors are overwhelmingly the dim, red, ancient, long-lived M-dwarfs that constitute the bread and butter of the galactic stellar population. The solar neighborhood is, in microcosm, a representative sample of the Milky Way. Mostly red dwarfs, a handful of more massive stars, some binary and multiple systems, a white dwarf or two, an assortment of objects at different stages of stellar evolution, moving slowly through space on their individual trajectories, occasionally passing close to each other and then drifting apart again. Conclusion. So this is the solar neighborhood, the stars closest to Earth, the stellar community that constitutes our immediate cosmic home. Within about 12 light years of the Sun, there are roughly 20 individual stars in about 15 stellar systems. Of those 20 stars, the overwhelming majority, 15 or more, are M-type red dwarfs, small, cool, long-lived, frequently flaring, and only now beginning to yield their planetary systems to our instruments. Several of those red dwarfs have confirmed or candidate planets, and the statistical picture strongly suggests that nearly all of them host planetary systems of some kind. The confirmed or candidate planets span a range from slightly above Earth mass worlds, inhabitable zones, to super-Earths, to Neptune-class objects, with no confirmed giant planets around any of the red dwarf systems so far surveyed. Among the brighter, more massive stars in the neighborhood, we have Sirius, the brilliant blue-white dwarf with its white dwarf companion, young and harsh, and Procyon, the yellow-white subgiant, also accompanied by a white dwarf. Neither is a strong habitability candidate. We have Epsilon Eridani, the nearest visible naked-eye star with a confirmed planetary system, a K-dwarf showing us what our solar system might have looked like in its youth. We have 61 Cygni, the first star to have its distance measured, a quiet binary of orange dwarfs whose historical significance is matched by their potential as habitable zone hosts. And we have Epsilon Indi A, an old K-dwarf with a directly imaged cold giant planet and the full weight of JWST's attention, one of the most promising targets for future Earth-like planet searches in the entire neighborhood. What this list of the nearest stars tells us, more than anything else, is that the solar neighborhood is not empty, not featureless, and not waiting to be explored. It is a pause already populated with a diversity of stars, architectures, and planetary systems. Some of them old and settled, some young and still forming, some quietly stable, and some violently active. The nearest confirmed habitable zone planet is around Proxima Centauri, 4.24 light-years away. The nearest K-dwarf habitable zone system with a directly imaged planet is Epsilon Indi A, 11.8 light-years away. The nearest star with a confirmed planetary system visible to the naked eye is Epsilon Eridani, 10.5 light-years away. These are not abstract statistics. They are places, specific locations in three-dimensional space, at specific distances, hosting specific physical environments, some of which may host something we have not yet found anywhere but here. The nearest stars are not the brightest stars. They are not the most glamorous stars. They are not the stars that ancient civilizations named and navigated by. They are mostly faint, red, and invisible to unaided eyes. But they are ours in a way that the distant, brilliant stars are not. They are the stars whose light reaches us first, whose gravity is most immediate, whose planetary systems are most accessible to our instruments, and whose surfaces, if any of them harbor life, would be the first to receive and return any signal we send into the dark. We have been looking at the wrong stars. The night sky's brightest lights are spectacular but distant. The real neighborhood, the stars within reach of any plausible future mission, the stars closest to our own small sun in this vast and mostly empty galaxy, is dim, red, numerous, and full of planets. It is out there right now, surrounding us in every direction, most of it invisible to the naked eye, but mapped in exquisite detail by instruments we have built and trained on the sky with exactly this kind of curiosity. The nearest stars are home, not in the sense of habitable or inhabited, though some may be, in the sense of being the defining geography of our position in the Milky Way. The sense in which you know your street, your neighborhood, the faces and names of the people who live nearest to you. We know our stellar neighborhood now, with a precision that previous generations could not have imagined. And what we have found there is stranger, richer, and more various than the night sky's brilliant but misleading advertisement suggested. The closest stars to Earth are out there right now, glowing, orbited by worlds, drifting slowly through the same spiral arm of the same galaxy that the sun drifts through. Most of them you will never see without a telescope. But now you know their names, their distances, their masses, their planets, and their futures. The solar neighborhood is no longer anonymous darkness between the bright lights. It is a mapped, known, and endlessly interesting place. And it is, within the constraints of physics we have discussed in other videos, the totality of our accessible cosmic home.